Hello and welcome to the University of Manchester, the birthplace of graphene and the global centre for its innovation and development. Our science heritage at Manchester includes the likes of Ernest Rutherford, Alan Turing and Beatrice Schilling, but graphene research brings us into the 21st century with materials and developments here in our laboratories. So it's British Science Week here at Manchester Museum, and we're going to head upstairs to see a demonstration of the graphene experiment that won the Nobel Prize for Physics in 2010.
So we're here at Manchester Museum and we're going to do the experiment to extract graphene from graphite, just like Andrei Geim and Kostya Novoselov did in 2004 as part of their Friday night experiments. So what you do is you take your graphite sample on your tape and you extract some onto some Scotch tape, just like they did. That's called exfoliation. And then you basically fold and unfold your tape a few times to isolate some layers of graphene on the surface of your tape. If you then stick it down on paper and then put it under the microscope, you can then see some thin layers of graphene. They use silicon dioxide as their contrast, but for our experiment today we'll just use some white paper and you can still see the thinner regions of graphene compared to the crystalline graphite. So we've just seen the experiment, which can be used to isolate single layers of graphene from graphite. What I'll now show you is a 3D representation of what we were doing with the sellotape. So each time the sellotape was being pulled back and forth, the layers of graphite, the graphene from the graphite were being separated, kind of like this. So they're being lifted off because the forces between the layers are really weak. Meanwhile, the forces between the carbon atoms within each layer are really strong. So that's why you get really strong, flexible, conducting graphene from your graphite. So one exciting area of research, which is a very hot topic at the moment in 2D materials, is being able to change the angle between two layers of graphene. So if you twist one layer, you can get a new structure appearing where you get a sort of a new type of lattice where you get these different correspondence points between the two layers. And as you change the angle, you can get all kinds of different patterns. And this is known as twistronics.
So now we've learned a bit more about how graphene was originally isolated, let's go talk to the academics in the NGI about the energy applications of graphene.
I'm a reader in nanomaterials in the Department of Materials, and my labs and my office are based here in the National Graphene Institute.
I am a research fellow and a lecturer at the Department of Materials, National Graphene Institute and Henry Royce Institute, University of Manchester.
My research area is broadly across two main areas. One of them is electrochemical energy storage. So I do work on batteries and supercapacitors and electrification of vehicles in particular.
My research group mainly focuses on exploring different applications where graphene can actually make a strong impact, for example, nanocomposites.
And the other side is on polymer nanocomposites, so that's looking at lightweighting and increasing the strength and materials properties of carbon fibre, glass fibre and other composites like that.
We know that graphene is a nanomaterial. Its dimensions are much smaller than the diameter of one of our hairs, and it is composed only of atoms of carbon, which means that it is very light in weight. As a consequence of these very small dimensions, its composition and particular structure of graphene, it has outstanding properties.
Probably the most important thing about graphene is its multifunctionality. It's the fact that we have its high mechanical strength, its toughness, its flexibility that allow it to improve mechanical properties of, say, composites. But alongside that, we also have its electrical and thermal conductivity. So that means that it's great as an additive, as I said, for energy storage or improving thermal management. But it's when we combine these properties together in graphene that makes it so unique. So we can improve the mechanical strength as well as the electrical conductivity as well as the thermal conductivity all at the same time.
So as probably you know, in 2010, two academics from the University of Manchester, Geim and Novoselov, were awarded the Nobel Prize in Physics, and the National Graphene Institute was built here in Manchester in order to promote and to develop both fundamental science of graphene and applications of graphene.
The facilities here are sort of world class. We have one of the world's largest clean rooms. We have a lot of different characterization equipment here to measure the properties of graphene. We have facilities here to manufacture graphene, and so we can do everything from producing it, characterizing it, putting it into applications, and then testing them. So having that all under one roof is quite unique, and we've really got a sort of a critical mass of different graphene researchers here that allow us to collaborate with people from physics, materials, chemistry, engineering, and the other departments across the university.
Some of the applications of graphene are actually structural and multifunctional nanocomposites for the aerospace and automotive industry, nanocomposites for electrochemical energy storage, devices such as photovoltaics, supercapacitors and batteries, as well as membranes for water filtration, gas separation and fuel cells.
So there are lots of different commercial products that have come out that contain graphene, a lot of which are sort of taking advantage of either of its mechanical or electrical properties. One of the most commonly seen examples are these trainers here made by Innovate, which have graphene in the sole of the shoes there to improve its toughness and sort of how long they last and improve the wear resistance.
There are already some applications of graphene on the market. For example, it's being used in the sports sector. It is actually being already incorporated into skis or trainers, for example.
And then another example from a few years ago was the watch that was made by McLaren Formula One team and Richard Mille. And this has graphene in the carbon fiber body of the watch as well as the rubber band. And at the time it came out, it was actually the world's lightest watch. And they cost about €1 million each. And they all sold out at launch, so they're rather rare and hard to find.
So graphene is also used as a 2D material to make atomic-sized structures and as an eco-friendly alternative in construction.
I'm a Royal Society University Research Fellow and a professor in the Department of Physics, and I work in National Graphene Institute as well. Concreting would be enabling sustainable future for building infrastructure. So it emits less carbon dioxide, and it makes the buildings stronger with less volume of concrete. So this is one of the newest applications which is coming out of graphene research. So I am working with graphene and 2D materials, and I use them for making nano capillaries and even 1 atom thin capillaries. So it's like a nano fluidic devices. That's what I make with 2D materials. So graphene firstly is 1 atom thin, and it is atomically flat. So I use it as a building block to create capillaries, almost like building these capillaries like a Lego-like assembly. So it's like atomic Lego. So you pick the material you like, either it is graphene or other 2D material, and so you have a variety of choice that you can get with 2D materials. The material can be conductive, insulating, or semiconducting, depending on whether it is graphene, boron nitride, or moly sulfide, or it could have properties like water liking or water repelling. So we get a variety of choice, and I use these building blocks to construct capillaries which are at the atomic scale.
If you want to learn more about graphene research at Manchester, visit these YouTube videos.